Hello, my name's Sam. I'm going to do another tech interview today. We'll do it in mock style, so I'll be using a Google Doc, which is horrible, but here we are, and that is how a lot of interviews tend to be. So we'll pick one at random from the easy and undone list, and let's see what we get and start the timer. So we've got a balanced binary tree, number 110, and they even give us some of the tree node code as well. And what we're trying to do is determine if it's height balanced. And here they even tell you what height balanced means. So the interviewer would probably tell you this as well. A height balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. Okay, so the idea is that you couldn't have like a really long depth along one side. So the height of the left one is 1. The height of the right is 2, let's say. So true. Here, the height of the right is 1. The left is 1, 2, 3. So it's false. And the number of, so here are some of the constraints that would be asked is like, how big could this tree be? Will it fit in memory? We're going to assume that this will all fit in memory. And in fact, the constraints are the max height of this tree is going to be 5,000, or the number of nodes is going to be 5,000. And the values within those nodes will be an integer under 100k or less. Okay, and we're past the tree as a array with the root, and the way they store it inside this array is, well, this is how they show it. They actually give it to us as a class instance of the class of a binary tree node where it has a left and a right value, a left and a right, and a current value. It looks like we don't actually care about the values for this question, just the height of the tree, and we're trying to figure out whether it's balanced. So I'm just going to copy this over here, just so we have it, and sure, we'll keep, well, let me pretend we didn't have access to that. So what I'd like to do is start thinking about the problem and kind of talk out loud how I'd like to approach this. So my first thought is whenever we have a tree and we're trying to calculate the depth of it, one of the ways you can do that is recursively. You call a function on the root, it calls the same function on its children, and eventually returns back a value once you hit some sort of requirement, in this case being the leaf node or the node without any children. So we have this concept of a leaf, and in this case it'll be if they have neither left or right children. And we want to return the current value. We don't even care about the value, we care about returning, if it's a leaf node, it's at the bottom, we'll call that 0, and every step up we're adding 1 to it, and that'll give us a depth. And one thing of note here is we technically only need to return whether or not this tree is balanced. We don't have to iterate through the whole array. If we were to, let's just say approach 1 brute recursive. If we were to iterate through the whole tree, we would be doing some sort of, well, it would be O of n for number of nodes, or O of d log d, I think, for depth, because we're doing in this case, this is a binary tree, so for every depth of the tree, for the max depth of the tree, we're doing log n depth searches. I think this might be right. I'm not entirely sure to check. Okay. The problem, though, is we might have a tree where the last two nodes are the same height. So we actually need to do a check for the height for both your children and make sure they're within range and return false if not. So instead of returning the depth, we're returning the depth and valid, I suppose. Yeah, I think so. So our height balanced. So let's do a function, check balanced, and our input's going to be node, which in this case is a tree node. And then the output's going to be Boolean for if it's balanced or not. So let's start with the base case. If not self.left and not self.right, then we're a leaf. So we're definitely balanced. So we'll start with the first one being balanced and the second one being our depth, or how high we are from our children, rather than depth. So that'll be 0. Then if we do have children, then we get the check balanced. Left is equal to check balance of self.left, and similarly we get the balance of self.right. We need to make sure that if not left or not right, if one of the children are not balanced, we just return false, because it's not balanced. And it doesn't really matter what happens from that point on. We could technically do this check for left. Left of 0. Left and left depth and right. Let's call it height instead. I think that makes a little more sense. And so if not left, return false. And if not right, return false. So both of them have balanced, both of the children are balanced now. And we want to check that these two children with each other have a height that's within one of each other. And that's the definition I think they gave us, which is it has to be within, doesn't differ by more than 1. So we can do a check of balanced equals left height minus right height, and the absolute of that is less than or equal to 1. So we now return the max, and then our height is equal to the max of left height, right height, plus 1. So we now return balanced and height. Okay. And I think that actually might get us to a working solution. You can even do a check here. It seems like the way they like to approach this is with an optional for the tree node, and we could even do the same here. So now if not node, we just return true and 0, and that way we don't have to do a check for the children. Okay. So what I'm seeing here is we are basically recursively calling our way through this tree. We're doing a left and a right check balanced. So the number of calls will be depth, log of depth, I believe, for the max length of the tree, or it'll be, well, you know what? I don't remember exactly how we do this. N log n? No. In the worst case, we're checking every single node, so we could just say for number of nodes. We're checking the number of nodes. I think that might be one of the ways that they're doing it here, considering the inputs. But more likely than not, it'll be smaller if it's an unbalanced tree. If it's a perfectly balanced tree, we end up checking all the nodes. So yeah, then we're not storing any extra information besides the true or false, but we are passing it through the stack. So I think in the worst case, we're storing O of, I think it's log n, space complexity. And here, might be completely wrong about this. I'll put this in the comments, or I'll check it after we submit. So let's have a look. So let's close this down, copy it over. Looks like we have our optional. make sure we have no tabs. If not node, return true. And here we're returning if valid and height. And we're just trying to make sure the heights, pardon me, stay the same. Check balance left, and we have to do with is balanced in this case, so absolute max, since these are just single values, these are still constant. Let's have a look and see what we get. Another approach I was thinking about at the time is, oh, not node. We have to change node to root. And these are not self. This is root.right. We need to make sure we actually call this node.left and node.right here. Okay, let's try that again. Oh, wrong answer. We got true when it should have been false in this case. So what's going on here? I have a feeling when we have null values, that means the tree ends at that point. So what would that result in? So root node has 2 children, values 2. This one has 2 children. This one has no children. And then one of these has 2 children as well. Are we not adding +1 at the right time? Before I get too stuck up on that, I just wanted to quickly say another approach is iterative, using a stack to keep track of, or a stack or queue to keep track of children nodes instead of doing a recursive call. One thing to note here is actually we're returning not just a bool, we're returning 2 things. And interestingly enough, that didn't seem to show up properly here. So let's create a sub function. That only uses the first value, and we'll do this for this too. And let's try this again. All right, I think that was the issue. I didn't realize that we had a function that was being called a returning bool, but actually it needed a sub function to handle the height as well. So keep that in mind next time. Create a sub function and then the actual function above it that uses that function. But that seems to be the case for there. Let's double check and see if this works for the actual submission. And it looks like we're good. Surprisingly fast as well, which is interesting. Unrelated, this shouldn't be, you shouldn't pay attention to this too much. Usually it has to do with the backend rather than anything special to the function itself, unless it's a more complicated one. Good to see, though. I think one thing we can talk about here, we're about 15 minutes in, is what are the advantages and disadvantages of using a recursive versus a iterative approach. With a recursive approach, it's a lot cleaner and easier to understand. You're just kind of calling yourself, but you're relying on stack memory. So if the depth of the array, if the depth of the tree is greater than stack memory, we have overflow, stack overflow. So in those cases, an iterative approach where you can store it in memory would be better. It can be a bit more complicated. So generally, you might be starting off an interview doing the recursive approach. But it's worth keeping in mind that, especially as you start to get into the mediums, that a recursive approach will probably have issues with it that you need to be aware of. All right, well, that was it for this one. Hope you guys enjoyed this, and feel free to leave some comments, and see you next time.